Hi, welcome back. In this lecture, I would like to go through a simple example of using OpenMP. The example is called MaxLoc for max location. And this example will showcase the usage of critical section and atomics in OpenMP. And also, we are going to look at some issues related to the performance of OpenMP when using critical sections. So not all the computation are simple loops that can be easily parallelized across threads. We saw an example in the previous lecture. The example that we are going to look at today in this lecture is to find the location and value of the largest element in an array. So basically, we will allocate an array, we will fill it out randomly, and then we will look for the largest value, in particular for the location of the largest value in the array. So the code is actually pretty simple. So we have an input vector called x, and then we have a loop going from 0 to n, where n is the size of the array. And for each array element, we basically check if the current element of x is larger than the current max value, right? So we go through all the array and found the value that is maximum and the location of the maximum value. So this is rather simple. We need to think about how to parallelize. So one of the issues related to this maxval and MaxLoc. So all the threads are potentially accessing and changing the same values, MaxLoc and maxval, right? So you're using different threads. MaxLocs and maxval are actually shared across threads. So it may be that different threads are trying to modify the value, right? So that each thread is finding its own value and is trying to update it. So of course we don't want to have that. We already talked about risk condition when talking about reduction. Here are the same things. We might have a risk condition. So OpenMP provides several ways to coordinate access to the shared values, right? Particularly, we have the pragma OMP atomic constructs that allows only one thread at a time can execute the following statement. The statement following the atomic construct. The second way is to use the pragma OMP critical that allows only one thread at a time executing the following block. What is the difference between atomic and critical? Well, critical is followed by a block of code, while OMP atomic is just one statement. So no block is just one statement. Atomic might be faster than critical, but mostly it depends on the hardware, but also in the implementation. So let's try to do this. So if I ask myself how to parallelize this, right? So we saw in the previous lecture that we can use the OpenMP parallel for, that is basically forking all the threads, and each thread is assigned to a block of the array, right? So what's the problem with this? Well, the problem is that each thread might update at the same time maxval and MaxLoc, right? So there is a risk condition. How do you fix this? Well, we introduce a critical section allowing only one thread at a time to update the values of maxval and MaxLoc, right? So here we have the loops, and then we add the pragma OMP critical. So at this point here on the top, we parallel for, we spawn the threads, and then the for construct is dividing the threads across the array. And then at this point, we wanted to have this piece of code to execute it by one thread at a time, right, to avoid the risk condition. So we add the pragma OMP critical, and then this is the part of the code included between curly brackets that is executed by just one thread at the time, right? However, critical section can be expensive when talking about performance. So the critical section is costly in two ways. Well, first of all, acquiring the critical section often requires a reading and writing from the memory, not just the cache, right? Just think how would you implement a critical section, right? So probably you have a variable, it's kind of lock, and as soon as the thread comes in, it changes the value of this variable, right? That is shared. Right. So critical sections are basically memory operation. Right. So this cost is unpredictable, but for sure includes the whole full memory latencies. The second important performance issue when looking at a critical section is that only one thread at a time can be within the critical section, right? So the code might serialize. So let's look at the performance results of MaxLoc using this following implementation, this slide. So these slides show the performance. On the x-axis, we have the number of threads. On the y-axis, we have the execution time in milliseconds. We have two lines. So we have the serial version, that is the orange one, and the blue one, right? So the orange one is the serial, so it doesn't change depending on the number of threads, and the blue one is actually is changing depending on the number of threads because it's our OpenMP version. This figure is very scary, right? So you see a few important things. First, that the serial version is always faster than OpenMP, right? So we parallelize the code using OpenMP with the expectation that our code will be actually faster, right? Increasing the number of the threads, we're going to have a speed up. But here we have a negative speed up, right? So you see that adding the number of threads, the performance of the code is getting worse and worse, right? So how is it getting worse? Well, there is some noise here and there, but it's basically linear increasing with the number of threads, right? We can also, so the other information we have from this plot is actually the cost of what is the memory operation adding a critical section. So for instance, here when we have just one thread, we can compare the cost of the serial and one thread for the critical section, and you see that the cost for one critical section is roughly 15 milliseconds, right? So a few comments about the plots. So for one thread, we have 1 million critical section because the size of our array is 1 million. So if we divide, so the cost is for 1 million is 12 milliseconds, right? This part. So that means that each critical section really pretty fast at 12 nanoseconds, right? So we divide 12 milliseconds by 1 million. That is roughly 10 clock cycle, right? So not bad actually, the way that a critical section is implemented in OpenMP. The scary behavior is actually this one, that we saw that near linear behavior as we are using more and more threads. So more threads take actually longer. So the hypothesis we have is that threads contending for the same lock are actually there. So the code serializes, and the extra overhead is coming from extra serialization that comes with the extra usage of threads. So how we can avoid the critical section? Well, the performance poor because we insist on keeping track of the max val and location during the execution loop, right? So we insist on having shared values, and each thread is responsible for updating them. So In reality, we don't care about the value during the execution loop, just at the end, right? So this is quite common source of performance degradation. The description of the method used to compute a value impose additional unnecessary requirement of the properties. So a better approach, instead of having like a share value, we could actually have a share array where each array element corresponds to that particular thread. And then each thread will calculate its own max value and put it in the array index equal to the ID. So the major idea for improving performance is remove dependency between the threads, so the dependency of these MaxLocs and MaxVal, right? And as I told you, the idea is having each thread to find the MaxLoc in its own data, and then later on combine it. To do that, we can use temporary arrays indexed by the thread number, so we can have a MaxLoc and MaxVal for each thread, to all the values found by each thread. A very simple example for doing this is the following. So we allocate two additional arrays, MaxLocs, with the size of the number of the threads, right? And then we parallelized. And in the parallel region here, so you have a OMP4, we store so we found first the value of we first find the value of okay, so sorry. So we open here the parallel region, and we have this array that are shared. We found the ID of the thread using this OpenMP function, and then we parallelize the loop here. So we are in a parallel region, and then here we are basically doing work shelling, right? We are just distributing across loop iteration, and here we store the MaxLoc. Instead of in one shared value, we store it in an array, right? So in an array whose size is the number of threads, and we store it at the element equal to the ID of the thread. And then after actually we found this array that stores the maximum location and the maximum value for each thread. We go through this smaller array, right? We can do this serially, and we found what is the maximum value in the MaxLoc, right? So here, for instance, so this part of the code is actually serial, it's not in the parallel region. So we first set up MLoc and MVal to the value of the first thread, and then we loop across all threads to check what is the value for each thread. So this is a plot with the performance of the new MaxLoc. Well, we make this extra array, and that is the share. And each thread is computing its own array element, right? So where the array element corresponds to the ID of the thread. So as you can see here, so these are tests done on BESCO. The good news that we are now in the position of being faster than the serial version, right? So is around this area here. Between 5 and 28 threads, we are almost like 4 times faster than the serial version, so this is very good news. We saw for a smaller number of threads, almost like a linear increasing of the performance, except for this jump here that is likely, some noise, probably some interference, right? So this part is basically linear, and then we saturate. So this is very good news. There is something funny on Basco when try to use the full number of threads equal to the cores, right? So the performance here jump up to the serial one. The question I have, can we do better? Very likely so, because otherwise I wouldn't pose this question. The code is simple. Each thread is referencing different elements in X and in MaxLoc and in MaxVal arrays. So the code to combine the final results only has 32 elements or less to look at. But there is a hidden dependencies. So something is actually shared, and what is it? Okay. So let's look at consider this very simple code. We have two threads. One is basically they're doing the same things, right? So we start from 100,000, and then we have basically a counter. And what we do, we just increase the value of A by 1, right? So thread 1 does exactly the same things, but for B, right? So it's doing this, is adding up to be 1,000 times. So the question is, how many times cache misses occurs? Well, simple model, what probably is starting in mind to us is actually that we pay the cost of full compulsory misses of N, M, and A and B, right? So that would be basically very, very nice, because we have A and B in the cache. We don't need to spend any time to go to the main memory, right? However, it is not really like that. And the problem is that the A, B, N, and M could be on the same cache line, right? And so if A, B, N, and M, in particular, if A and B are on the same cache line, rise to on one cache line would force other cores to other threads working on the same cache line to revalidate their cache, right? So the cache will be all evicted and then will be basically updated, right? So a very simple example here is that if A and B are on the same cache line, it might happen that thread 1 is writing to A, right? Like in this case, here is writing thread 0 is writing to A, but thread 1 even must revalidate is the cache line, right? Because the cache line has been updated in A but not in B, even though the thread 0 is not updating B, right? So this is due to a cache protocol that requires the revalidation of the cache if a value within the cache line has been updated, right? So in this case, if instead of having 4 cache misses, there are many as actually 200,000, one for each access of either A or B, right? So if A and B on the same cache line, an update on one thread of A will probably revalidate the cache from thread 2 because the cache line has been updated. So this is actually is not correctness problem. So that this is just following up a protocol for updates of the cache. It is actually a performance problem, right? So how can actually we can fix this? Well, common ways to alleviate fault sharing actually include storing a thread local results to update to a shared space once the computation is completed. So one way we could do to solve this problem is that instead of using a shared array, so for instance, we have these MaxLoc and MaxVal as array, right, where the maximum index is equal to the number of threads. Instead of having that shared, we can actually store a value within the thread. So this technique is called privatization of the thread, right? So we store in this private variable in the thread what is the maximum val and max location, and then at the end of the computation, we copy it back to the shared variable, right? Another way is actually to use padding. So spacing continuous memory blocks that are shared, so they are not on the same cache line, right? So we had some padding to our array that are including maxval and MaxLoc. So we enforce that we are using all the cache line, right? So we are wasting some of the cache line because with the padding, but on the other hand, we avoid we avoid the fault sharing problem. So one technique I did for this is actually to do some pad. I collect val and lock now in a structure, right, and include this padding of 128 byte, right. Then I make an array of a structure called max info, right, and then I basically do the very same things, just updating. So each thread will have its own max info structure that is updated. So if I do that, then the performance is the following. So you see that with padding we have roughly 10-15% difference. So is not much improvement, meaning that probably the file sharing problem here is not as severe in our cases. Nevertheless, 10-15% improvement is actually quite good when we're talking about high performance computing, right? So we will do all these different steps for your assignment, so I don't spend much time for this. This is the last slides. Next slide, I would like to look at another example on basically how to calculate pi with the OpenMP, putting together all the things we learned in this lecture and in previous lecture. So talk to you soon.